They're generally referred to as mass-to-mass calculations because we start with a mass of a known, and then via moles, we work out the mass of the unknown. So this is a very common way of doing chemical calculations. So the example here is to calculate the amount of iron needed to react with oxygen to produce 3.5 grams of iron oxide. And we're given the equation, so we don't have to worry about balancing. We want to produce 3.5 grams. And we know that we can't calculate with just masses, we have to calculate with moles. So if we want 3.5 grams, our first step would be to determine how many moles that's going to be. And to find the number of moles, remember that moles is equal to the sample mass divided by the molar mass. So I'm going to need to calculate the molar mass of iron oxide. So off to my trusty periodic table to find out the relevant atomic masses of the elements in my compound. But if I look in here, I can just do a shortcut. I'm going to need 2 lots of iron and 3 lots of oxygen, Fe2O3, and this will give me a molar mass of 159.7 grams per mole. Now I know the molar mass of the iron oxide, I can work out the number of moles I want to make using this relationship here. So my moles of iron oxide is going to be the sample mass divided by, make that one look a bit more capital, by the molar mass. 0.0219 moles. Okay, now I know how many moles of iron oxide I want to make. I'm going to just look back at the question to remind me what I'm supposed to be finding. It's the amount of iron that I need to find. That's what I'm trying to find. So at this point, I need to go back to the balanced equation and look at the mole ratio. So the iron to iron oxide, and when I say the mole ratio, what I'm specifically interested in are the coefficients. Okay, that's the ratio in the balanced equation. Now sometimes students get these around the wrong way, or get a little bit confused as to what to do with as the next step. So this is telling me that if this is how much I actually want to make, 0.0219 moles, the mole ratio tells me I actually need twice as much of iron, don't I? Twice as many moles. So what I'm going to need is 2 times this. Another way of thinking about it is like it tells you on page 35, that what you're going to multiply your, so this is a different method to arrive at the same calculation. You take your answer here, and then you're going to multiply it by the required, which is the iron, divided by the given, which is the iron oxide. So if I look at the coefficients using it this way, then it becomes 4 divided by 2, which is still multiplying that by 2. Okay? And I can always double check. Does this make sense? That if I want to produce 2 moles, the number I come up with, or if I want to produce 0.219 moles, this number is bigger, the iron is bigger, so the number of moles I need should be bigger. Now it might all seem like I'm labouring a pretty straightforward point here at the moment, but as calculations get more complicated, that's when students get a little bit more muddled and start to forget what they're trying to achieve. So from here then, my moles of iron are going to be 0.0418 moles. And it's a matter of working back. We wanted to know how much. When it says how much, it means mass. If it wants to know moles, it will say how many moles. And so we're going to use this arrangement rearranged to find the mass of iron, which is then going to be the number of moles multiplied by the atomic mass of iron, which we already found up here. So it's mass to mass because we started with a mass, we ended with a mass, but all of our calculations are done with moles because we know we need to match up the number of reacting particles. Okay, so there's lots of examples of doing these calculations. It's pretty important to get this straight. Have a go at those for the next few minutes.